recording. All right, so what we're going to talk about today we're going to talk about two different types of models today that they have a very similar purpose, which is to compare or to estimate. Well, we'll talk about the interpretation of the models, but I suppose you would say that the purpose is to model the probability of an observation belonging to one of J categories where J is greater than 2. So we have situations where we still have a categorical response, similar to what we had in the binomial, or similar to the data sets that we were exploring in the case of the binomial model. We want to estimate the probability the observation belongs to one of these categories. We can't use a logistic model because we have more than 2 categories. That's the underlying crux of it. The model that we're currently discussing, and I had introduced last class, is the nominal logistic regression model. So it even has logistic in the name. This particular model is utilized when you have a response variable that has capital J categories, but there is no order to the categories. From this type of model, we are able to get estimates of the log odds and therefore the odds of observing a particular outcome. And we are also able to get estimates of the odds ratio, which is essentially just the odds of one event given a particular exposure to the ratio of another event given the absence of that exposure. Okay. So to demonstrate this particular model, we are going to use this car preferences data set. Okay, and we're going to see this data set in 2 different situations today. The one that we are currently discussing, and in a situation where we treat the response variable as an ordinal quantity, which I think in this particular case, you can argue pretty easily it actually is, but it works well for demonstrating the nominal model as well. So in this particular response, we have, or in this particular data set, our response is whether or not the persons that took part in this particular survey rated the importance of various car features as no/little importance, important, and very important. All right, so I believe that the exact features that are of interest to us are power steering. Yeah, so power steering and air conditioning. So this data set actually might be quite old, because someone who doesn't care about power steering would be very surprising to me. Not having power steering would be ridiculous. Okay, so anyways, that's what they're rating. So it's the importance of whether or not a car has power steering and air conditioning, which I would also, this data set must be quite old, because air conditioning, I don't think any new car wouldn't have air conditioning in it. But anyways, so there's 3 outcomes: no/little importance, important, and very important. And the explanatory factors for the data set are the sex of the individual and the age group of the individual. So we have 3 qualitative variables. And then for each of the different interactions between the explanatory values, so for example, women 18-23, women 24-40, women 24 to 40, women greater than 40, we have a sample size that we've observed, and then we have how many people voted for or selected one of those particular outcomes within each of the those different interactions, right? So for example, if we consider women that are 24 to 40, there was 45 of them in total. 15 of them selected very important, 21 selected important, and 9 selected no/little importance. All right. So what we want to do is model the outcome category, so no/little, important, and very important as a function of the sex of the individual and the age group in which they fall into. So we're going to do this using the nominal logistic regression model. So this again is a a natural choice when you want to model a categorical response where there's more than two categories. In this case, we have three categories. The model, which we learned how to fit yesterday in R, is given on slide 14. This I here should be a 1. Okay, so that's pi 1. Okay, so what this model is showing us is the log odds of a person being in the jth category. So when j is equal to 2, this would be important. And when j is equal to 3, this would be very important with respect to no/little importance. Okay, so here we have, so pi 1 represents the reference level, which is how we know this. And we've designated the reference level as no/little. So we could say, for example, here, pi 1 is no/little. Pi 2 is equal to important. And pi 3 is equal to very important. All right, so that's the model that we're fitting in this particular example. And again, we learned how to fit this yesterday in R, and we learned how to set the reference levels for that particular example as well. Because again, if we don't set the reference levels, the model fitting process will automatically set defaults for you, and that might not line up with what we're actually doing in the lecture. In terms of the assignment, that doesn't really matter as long as you're able to interpret what the reference is based off the output. But if you do want to set your own reference level so you can interpret the model in a way that you think is most appropriate, you do have that ability. So for our particular model, we are modeling the log odds of important to no/little importance and very important to no/little importance, using x1, where 0 is going to represent the female sex. So that's our reference level. And then x2 and x3 are age indicators. So we're using 2 indicators for 3 different levels. We could set the model up using a 3-way indicator as well. That's perfectly valid too. In this particular situation, we're using 2 different indicators. And for both indicators, we are setting the reference level to be the youngest age group, which I think is, for that particular value, is a logical decision. So when x2 and x3 are 0, that indicates the youngest age group, which is 18 to 23. And then x2 when equal to 1 will represent the 24 to 40 age group. And x3 when equal to 1 would represent greater than 40. All right, so the model parameters are given on slide 15. Now, in addition to the model parameters, we have the standard error that is associated with said parameter. So we could use these to compute a test statistic. We also have the odds ratios that are computed using the estimates of each model parameter. And we have a corresponding confidence interval for that parameter. If the confidence interval includes 1, as these confidence intervals represent odd ratios, that would essentially mean that the odds of experiencing a particular outcome given a certain exposure is not different to the reference level. Okay, and we'll talk more about that momentarily. All right, so let's break down some of the things that we can pull out of this kind of model, as it does contain quite a bit of information. All right, I'm just going to get a few definitions pulled up here. Okay. All right, so I'll start writing it on this slide just so we can have some of the output here. Let's start with one of the intro examples. So for example, when All right, so for example, let x1 equal x2 equal x3 equal 0. Okay, so this would be women 18 to 23. Okay, so we have two different sets of predictors here, right? So let's say that we consider the first set, which is the log pi 2 to pi 1. So this is going to be negative 0.591. Okay, so this is the log odds of women 18 to 23 who rank the features as important to not important, right? So that would mean that the odds, so pi 2 over pi 1 will be E xp to the negative 0.591, which is equal to 0.5537. Okay, so this would be the odds of the event described. Right, so that would be, and we can do the same thing for very important with reference to no/little importance. So in that situation, we could just take log of pi 3 over pi 1. And then if we set everything equal to 0, we're focused on women in the 18 to 23 age group. Okay, so we can continue to use this preliminary structure of the model to find the log odds and the odds of particular events. So for example, let's say we consider let x1 equal 1, x2 equal 1, x3 equals 0. Okay, so now we are considering men who are aged 24 to 40. Right, and this is going to be a very similar idea. Like, so again, for illustrative purposes, let's suppose we take pi 3 versus pi 1. So this is going to be negative 1.039 minus 0.813 plus 1.478. Okay, so that's going to be negative 0.374. Okay, so then from this, we have pi 3 versus pi 1 is going to be exp negative 0.374. Okay, so that's going to be 0.688. All right, and then that is going to be the odds that men aged 24 to 40 rank the features as very important versus important. All right, so that would be, I guess in some sense, this would be one of the easiest things that you can draw out of the model, because these are direct, these are found directly by just plugging in the age group and the gender in this particular illustration that is of interest to you, and finding the odds of them ranking either important or very important with respect to no/little importance. Sorry, this would be versus to not important. Okay, does that make sense? Any questions? Okay, so the other thing that we can pull out of this output are the odds ratios. So these are going to be the odds ratio representing a particular gender and age group's preference with respect to the reference level, with respect to the preference of the reference level. So for example, let's say we consider, well, let's start with an easy one. So for log pi 2 given pi 1 is equal to, okay, so we'll have log pi 2 pi 1 is equal to negative 0.591. Okay, so this is x1, x2, x3 equals 0. And then we have versus log pi 2 pi 1 equals negative 0.591 plus, or I think it's minus, minus 0.388. Okay. Okay, I'm just going to take this part out. Hopefully it's clear. I just want to make myself enough space. Okay, so let's say that we compare these two models. So the only difference between these two models is that x1 is equal to 1. All right, so then from this, we would have the log of pi 2 over pi 1 minus the log of pi 2 over pi 1. Oh, there's a bit of a damn, sorry, I just need to kind of indicate which groups I'm talking about so it's clear. So this will be the reference level. Okay, and then this would be when x1 equals 1. That'll work. Is equal to negative 0.388. Okay, so that's the coefficient for B1. Therefore, the odds ratio for x1 equal 1, I guess we can write it like that, is equal to exp to the negative 0.388, which is equal to 0.68. Which is equal to. Okay, so that first coefficient is giving us the odds ratio comparing the odds of men in the 18 to 23 age group who rank the features as important versus no/little importance to the odds of women aged 18 to 23 ranking the features as important to not important. Okay, so this is odds of men aged 18 to 23 ranking features of cars as important versus not important to odds of women aged 18 to 23. Okay. Now, in this particular situation, we also have a 95% confidence interval. That 95% confidence interval includes 1. Okay, so we can say, since 95% CI for OR x equals 1 includes 1. That means that the odds of men ranking the car preferences as important versus not important is no different from the odds of women ranking the car preferences as important versus not important. Okay, and then similarly, just for illustrative purposes, like let's suppose that we can do this for all of the different groups and every single coefficient is with respect to that reference level. So for example, let's say we took beta 2, 3, okay? So this is equal to 1.478. Okay, so then the odds ratio here is with respect to x 2 equal to 1. Okay, so this is equal to 4.38. All right, so this is odds of men aged, or no, sorry. This would be odds of women aged 24 to 40 versus women aged 18 to 23. With respect to very important versus not important. Okay. And then in this particular case, you can see that the CI does not contain 1. it actually contains values that are greater than 1. So in that situation, it indicates that the odds of a woman ranking the car preferences as very important versus not important increases when they move into the next age group, which might be a logical conclusion or an expected result. Okay, so we can say here, since 95% CI has bounds greater than 1, this indicates odds of very important to not important increase for women aged 18 or aged 24 to 40 versus 18 to 23. Okay. Any questions? Does that make sense? Okay, I'm not seeing any. All right, there's one other thing I want to talk about in regards to interpretation. So these are direct interpretations of the coefficients. We could also build odds ratio interpretations comparing different levels within the experiment or comparing different gender age group combinations to the reference level. So there's a lot of different odds ratios that we can get out of this particular data set. And they're not terribly difficult to calculate as long as you're basically just subtracting off coefficients and then taking the exponent of those differences. But the coefficients of the model give you direct odds ratios with the particular indicator being active with respect to the full reference level values, which is what the beta 2-3 example that we just worked through is representing. So that was just an illustration for the situation where we considered that particular example, but we would have a similar definition for the remaining coefficients as well. All right, the other thing we need to talk about is extracting the probabilities of a particular observation belonging to one of the groups. So one of the things that we can get out of this model are the probabilities that a person belongs to one of those different groups, or the probability an observation is going to vote for a particular preference rating given the group that they belong to. Okay, and that's shown here. Okay, so these are the probabilities that n will vote for a particular rating. So this is saying, for example, we would expect that 52.4% of women aged 18 to 23 are going to vote no/little importance. 29% of women aged 18 to 23 would vote important, and 18.6% of women aged 18 to 23 would vote very important. Okay, so we can extract this information from the model. Okay, and this is kind of I like these problems. They're sort of fun little mathematical problems. Okay, so we're gonna start with extracting these three values here. Okay, so this is going to be example 1. Okay, and I'll just write it off to the side here. I didn't give myself enough room as per usual. Okay, so the first thing that we can do, and this is going to help us in all of the situations, is we can say pi hat 1 plus pi hat 2 plus pi hat 3 must be equal to 1. And this would be true regardless of the problem and the number of categories you have, right? So you might have 5 different categories. All the probabilities would have to sum to 1. Okay. So then we would have, because we're considering the reference level group right now, we would have log pi hat 2 over pi hat 1 is equal to negative 0.591. And we have log pi hat 3 over pi hat 1 is equal to negative 1.39. Okay. So what we're going to do here basically is just rearrange these to get an expression for pi hat 2 and an expression for pi hat 3 in terms of pi hat 1. Okay, so this will be 1 and this will be 2. Okay, so from 1, we have pi hat 2 is equal to exp of negative 0.591 of pi hat 1. Okay, so that's going to give us 0.5537 pi hat 1. And then similarly, from 2, we would have pi hat 3 is equal to 0.3538 pi hat 1. Okay. All right. So now what we can write is pi hat 1 plus 0.5537 pi hat 1 plus 0.3538 pi hat 1 is equal to 1. And then we can say pi hat 1 is 1 plus 0.5537 plus 0.3538 is equal to 1. And then we can write pi hat 1 is just going to be 1 divided by that sum. Which is equal to 0.524, right? And that's what we have in the solution. And then we can do a similar thing, like, so say pi hat 2, we can just take this and plug it into number 1. So this is going to be 0.5537 times 0.524, and that's 0.5537 times 0.524 which is 0.290. And then pi hat 3 would be 0.3538 multiplied by 0.524, which is going to be 0.186. So that's how we can compute the probabilities, and we can do the same things for the other groups as well. I wanted to give another example. So let's say, I don't know, let's try this one. Okay, so that'll be example 2. I apologize for the spacing. Okay, so this one is going to be log pi hat 2 over pi hat 1. Okay, so this is going to be men. So we have x1 equal to 1, and we have x2 equal to 1, and x3 equal to 0. So this will be negative 0.591 minus 0.388 plus 1.128. Okay, so we have negative 0.591 minus 0.388 plus 1.128. Okay, so that's 0.149. Okay, and then we have log pi hat 3 versus pi hat 1. Okay, so that's going to be negative 1.039 minus 0.813 plus 1.478. Right? So now we have these two expressions, and from this point, it's basically the exact same process that we just went through. So we can rearrange each of these to get expressions for pi 2 and pi 1. So for example, and so this will be 1, 2. So from 1, we would have log, or sorry, exp 0.149. So we would have pi 2 hat equals 1.161 times pi 1 hat. And then from 2, we would have pi 3 hat is equal to 0.688 pi 1 hat, right? And then I'll just stop here because it's from this point, you should be able to verify the probability. So from here, we're literally just following the same process we had above. We now have two probabilities with respect to pi 1 hat. We can plug them into pi 1 plus pi 2 plus pi 3 equals to 1, and then solve for pi 1, and then just use each of those to solve for pi 1 and pi 2. And what we should get out from that are the three probabilities that are shown above. Okay. I apologize for the spacing. I'll have another slide next time. Any questions? Okay. Okay, so for the fitted model, the minimal model, and the maximum model, I've given a number of different summary statistics on this slide. We're going to talk about the calculation of a few of these momentarily. One of the notable ones is this value here. So this is the log likelihood for the fitted model. This is -1/2 the deviance residual from R. Okay. So in R, when you use the multinom function, which we talked about yesterday, and then you compute the summary statistic for, I just want this to be very clear. So this is from R. Okay. So that's like the programming language. So when you run the multinom function in R and then you produce the output from the function, it gives you a residual deviance and an AIC. The AIC matches exactly what we have on this slide, right? So we know that the AIC is -2 times the log likelihood plus 2p. So we can extract the log likelihood from the AIC, which is what we've been doing in the past anyways. This is very easy to do here. So for example, we have 8 parameters in the fitted model. So if we took the AIC, which is 596.7022, right, we subtracted 2 times 8, and then we divided that by -2. Right, so we have 596.7022, which is equal to -2 times the log likelihood plus 2 times 8. So that means -2 likelihood is equal to 580.7022. So the likelihood is equal to -290.351. So if we extract the likelihood from the AIC like we did here, we can also show in R the deviance residual that is produced is actually -2 times this. So from R, the deviance residual, or residual deviance as it's called in the output, is -2 times the log likelihood, which is 580.7022. Okay, so just keep that in mind when you're working with the output, particularly on assignment number 3, because you don't want to confuse the deviances. So you'll notice that the deviance that I have given below is 3.94. I'm going to show you where that comes from momentarily. Okay, the other values, so for example, C, which is our value to test the fitted versus minimal model, that's computed in the normal way. So this is, for example, 2 times the log likelihood of the fitted model plus the log likelihood of the minimal model. So you can easily verify that by taking the difference between L and L min and then multiplying by 2. The pseudo R squared is also found in the same way. So that's the ratio of L min minus L divided by L min. So again, easy to confirm that value. And then we talked about AIC. And then the BIC here, this is going to be negative 2L plus P log N. And for this particular experiment, N is equal to 18. So that's the number of unique categories. Okay, so the sample size here represents basically a count of all the different outcomes. So women 1823, women 1823, men 1823. Sorry, how does women 1823 not important, women 1823 important, women 1823 very important. Yeah, that's how it works. Okay, and then you can actually see the list of that given above. So basically, it's just the number of observations is the total number of outcomes. So gender times age, the gender outcomes times the age outcomes times the rating. So 2 times 3 times 3 in this case. So this is gender, age. Okay. Any questions? Okay, so the last thing I want to do is talk a little bit about inference for the model. So we have a number of summary statistics put here. So there's two main tests that we can run based off those summary statistics. So we can test of minimal versus fitted model. So we have H0, minimal model is sufficient versus HA, maximal model is required. We have alpha 0.05. Okay, our test statistic is going to be C, which is the 77.84. Okay, and then our critical value for this particular test is going to be a chi-square on P n minus 1. P minus 1 degrees of freedom, right? Oh, okay. Okay, so this is going to be on P minus P min degrees of freedom, comma alpha. So this is going to be a chi-square on 8 minus 2, 0.05. So this is a chi-square on 6, 0.05. Okay, so that's 12.592. And then we can also show, or we can calculate the p-value. So the p-value for this particular problem is going to be basically 0. Yeah, so this is 9.9 974 times 10 to the negative 15. Okay, so then we would reject H0. Okay, so that means that at 5% significance level, data provide sufficient evidence that fitted model is required. Okay, so that's the first test based off of the output that we have. Okay, and then now for the deviance. So this is very important. Again, the output in R gives you that residual deviance value, which is basically 2 times the log likelihood times a negative. Now we want to compare, when we're using the deviance, what we are doing is testing the fitted model versus the maximal model. So we have here test of fitted versus maximal model. Okay, so what's going to happen here, and this is our classic deviance test. So we're going to have H0 fitted model sufficient versus HA maximal model required. Okay, so then on step 2, we have alpha 0.05. Okay, and then on step 3, what we have is for the deviance, we're going to compare those two deviance values given in the output. So this is going to be 2 times the deviance for the fitted. Oh, sorry. This is going to be 2 times log likelihood minus log likelihood max, or max minus log likelihood, right? Yeah, sorry. 2 times L max minus L. So this is 2 times, and then we have 288380 plus minus negative 290.35. Okay, so we have minus 288.380 minus negative 290.351. And that is where the value 3.94 comes from. Okay, so that's our deviance for the test of fitted versus maximal. Okay, and then on step 4, if we take the critical value approach, we have a chi-square on n minus p, or this would be like p max by minus p, right? So let's do p max minus p alpha. So this is going to be a chi-square on 4, 0.05. So that's 9.488. And then the p value, okay, is 0.414. So then we do not reject H0. And then on step 6, we would say at 5% sig level data do not provide sufficient evidence that the maximal model is required, right? Which is good. So basically the two tests are agreeing. They're both giving evidence that the fitted model is sufficient. Okay, so C is doing it with respect to the minimal model, and D is doing it with respect to the maximal model. All right, any questions? Okay. So this was lecture set number 7, which was focused on the nominal logistic regression model. So this is the function that we fit through the multinom, or this is the model we fit through the multinom function from the R package NNet. And we talked about the fitting of this yesterday in lab, but we hadn't seen interpretation yet. But all of the values here, so if you go back and compare to the code, all of the output values shown here will be the same. And then if you compute the fitted values, you will get the probabilities shown here. I forgot to mention this. So first off, the residuals here. Okay, so this is the observed minus expected divided by the square root of the expected. So you can compute those directly from the values given in the table for all of the different outcomes. This value here is little n times pi hat, where little n is the value that's given in the original table. So for example, for women aged 18 to 23, little n is 45. So this first value, 23.59, is 45 times 0.524. This value is 45 times 0.29, and this value is 45 times 0.186. Okay, so that's where those values are coming from. Any questions? Okay. All right. So the last lecture set that I wanted to discuss today is it's a fairly short set. It's on the ordinal logistic regression model. So these, I'm going to introduce you to a variety of different models, and then we're going to talk about the output from the most common type of ordinal logistic regression model, which is the proportional odds model. This is the model that's typically fit by default and in R and other software languages. So this is the model that I'm going to illustrate, and then we'll see in lab. The only difference between the ordinal class and the nominal class is, again, that there is an assumed ordering of the response variable. So the ordinal model would be utilized when the categories of J should have a rank to them. So technically, you could argue that for the card preference data set, there is a natural ranking of the response variable, which would be no/little to important to very important. Okay. All right. Now, as mentioned, there's a number of different ordinal models that could be considered. So I'll just very briefly go through these. The first one is the cumulative logit model. So here you can see that we're defining the probability that Z is less than some cut point CJ versus Z being greater than some cut point CJ. Okay. And then this logit model is given by the following. So we have the log odds of pi 1 to pi j versus pi j plus 1 to pi capital J. And that's going to be equal to some linear predictor. Then we have the proportional odds model. The proportional odds model in terms of output is the most similar to the nominal logistic regression model, which is probably one of the reasons why it's considered the default model in most packages. So you can see that the way that this model works is you have, again, a ratio of some jth categories to the remaining jth categories. That's linked by the following value. So you have the same slope for each of the different explanatory terms, and you just have a different intercept representing the levels of interest from the categorical response. And like the nominal logistic regression model, the output of the coefficients is exactly the same. So they're representing odds ratios between the jth groups and the reference level, whichever that might be for the particular situation. Okay, another possible model is the adjacence category logit model, which is shown here. So fairly similar to the other two. Here we have the log of pi j versus pi j plus 1 has the following linear predictor, and we can simplify this to log pi j over pi j plus 1 given the value shown below. Okay. The continuation ratio logit model, similar definition. So you can see that we have here the log odds of pi j versus the remaining categories. This would also be a fairly intuitive model, I think. And it's equal to, again, some linear predictor based off of J. Okay, so we are going to use the car preferences data to illustrate the proportional odds model. Okay. Okay, so this is the exact same data set that was given in the previous illustration. You can tell it's the same data set because I copy and pasted the slides. All right. So in this situation, we have the following proportional odds model. Now you can see here that the setup of the model is a little bit different from what you might expect. So there is a bit of a trick in terms of how you would interpret the outcome from this particular model. So for example, you can see we are modeling the log of pi 1 to pi 2 plus pi 3 as a function of the following linear predictor set. And then we're modeling the odds of pi 1 plus pi 2 to pi 3 as a function of this linear predictor set. Again, what's convenient about this model is that we have beta 1, beta 2, beta 3, which are consistent across both models. And then we just have a beta 0, 1 and beta 0, 2, which represent the intercept of the different odds that are of interest to us. Now, again, the beta 1, beta 2, beta 3, those represent the log odds of experiencing a particular outcome, which in our case is still no / little, important, very important, with respect to not important, given a particular indicator is in effect, or given that a particular effect has been triggered, which for us, again, just means either men versus women or the age groups. All right, so here's the output for this model. So you can see we have the following set of values, right? So beta 0, beta 0, 2, beta 0, 1, beta 0, 2, beta 1, beta 2, and beta 3. Okay, so for example, so for beta 0, 1, this is the log of pi 1 versus pi 2 plus pi 3 is equal to 0 0.4, 0 0.044. Okay, so this is when x1, x2, and x3 are all equal to 0. So this would represent the log odds of women aged 18 to 23 selecting no slash little to important and very important. Okay, and then for beta 0, 2, we would have log pi 1 plus pi 2 over pi 3, 1.655. Okay, and then this would be very similar, log odds of women aged 18 to 23, selecting no slash little and important to very important. All right, and then again, as described above, each of the coefficients are the log odds or the odds ratio for the jth category. Yeah, so we should be able to show that is true. I guess it would just be consistent across each of the different definitions. So you would have for beta 1, you would have exp of beta 1 hat which is 0.56. So this is going to be odds ratio value for odds of men aged 18 to, or sorry, men aged 24 to 40 versus odds, or sorry, 18 to 23 versus odds of women aged 18 to 23 who select no / little to important and very important and it would be the odds ratio of the other combination as well. Who select kind of think that the nominal one is a little bit nicer to work with personally, but based off of the direct interpretation of the model, this is what we would be dealing with. Okay, and then we can also extract, so you can see here again, I've built the same table I did before. So we can also extract from this the different probabilities. Okay, so again, we have pi hat 1 plus pi hat 2 plus pi hat 3 is equal to 1. And then we would have, so from the previous slide, I'm just going to grab these two things here. Okay, so from this one, we would have pi hat 1 is equal to 1.045 pi hat 2 plus pi hat 3. And then from this one, we would have pi hat 1 plus pi hat 2 is equal to 5.233 times pi hat 3. All right, so then what we can do is say 5.233 pi hat 3 plus pi hat 3 is equal to 1. So that means that pi hat 3 is equal to 0.160. Okay, so then we would have pi hat 1 plus pi hat 2 is equal to 5.233 times 0.160. Which is 0.8 3, 7. Okay. So then from that, what else could we extract? Or I guess that should be 0.84. Oh no. Yeah, you could get that from the above one as well. I don't think this one is going to help us. I did this before. Oh, I see what I did. Okay, so then what we could also say is we can write pi hat 2 plus pi hat 3 is pi hat 1 over 1.045. So then we have pi hat 1 plus pi hat 1 over 1.045 is equal to 1. So this would be pi hat 1 is 1 divided by 2.045. Wait, sorry, that's not correct. Pi hat 1 equals 0.511, and then pi hat 2 is equal to 1 minus 0.511 minus 0.160, which would be the 0.329. Definitely not easier to work with, but we can extract the same information. Okay, so only a couple of minutes left here. Does anyone have any questions? Okay, so all the output in the table is exactly the same as it was before. So the expected values are the pi times the n for each age group. The residual value is observed minus expected divided by the square root of the expected. If we sum those values together, if we sum the square of those values together, we should come up with 4.564. And then on the next slide, I give the same kind of output that we had before. Everything is defined in the same way, and you can tell that the values are actually extremely similar. Like these two models are giving pretty much the exact same fit based off the data. So we can run the same inferential procedures that we had discussed before, and we can show the values work out in the same way that we had discussed before as well. So I'll finish this up and I'll post the solutions. And when we come back after the break, I'll review the solution to this, and then we'll start with the Poisson model. So have a good reading week. And I will see you guys in person when we come back on March 1st for our first class.